Okay, so today I want to talk about a 2D vectors problem, and in this case it has given us multiple displacements that we have to all add up to find the total displacement from the starting point, as well as the total distance traveled and the direction of the most direct route back to the start. So first thing I'm gonna do is put a compass so I know my directions and what signs I'm gonna associate with them. So north will be positive, south will be negative, east will be positive, and west will be negative. Now I can start drawing my diagram, and this is going to be a pretty complex diagram because we are given 5 displacements. So first displacement, actually I could write this down first. So first displacement is 50 meters north, 47 west. What that basically means is, let's say we start here. We're looking north and we stray 47 degrees west. So you can kind of just imagine that. This is the north axis. And then we stray 47 degrees west. West is left. So it looks something like that. And this angle touching the north axis would be 47 degrees. We can label this as D1, 50 meters, and we're gonna have to break this up into X and Y components later. So what I like to do is I like to label the hypotenuse and the adjacent just so I can remember it for later. This is our starting point. In this case, the angle is touching this line, so this is the adjacent. So our adjacent is going to determine how far we move on the y scale or the y-axis, and the opposite here is actually going to determine how far we move on our x-axis because it's moving horizontally and this one's moving vertically. Okay, move that down a little bit. Okay, now our next displacement is 22 meters. Oh, is 22 meters west, 43 degrees north. And same as the other question, you go from the previous vector and you look west, so this way, and you tilt up because it's north 43 degrees. So it's gonna look something like this. Actually, I'm gonna have to move this to the side. So it's gonna look something like this. We're looking west, we tilt up 43 degrees. And then that angle inside there, let's just label our axes. So this angle here is going to be 43 degrees because we're looking west and tilting up 43 degrees. We can now label this, we're going to have to break this into X and Y components later too, but we can now label this as D2, 22 meters. As I do before, I like to label the hypotenuse and what the opposite and adjacents can be associated with. In this case, our adjacent, the one that's touching the angle, is going to be our x-axis, and our opposite is going to be the y. Okay, Now our third displacement, so we did this one, did this one. Our third displacement is 30 meters east, 60 degrees south. So what does that mean? Like the other displacements. This first value here tells you where you're looking at first. The angle in the middle tells you where you're going to shift, but the direction at the end is tell you where you're going to shift to. So displacement 3, 30 meters east, 60 degrees south. That's basically saying 60 degrees south of east. So I'm just gonna move this over again so I have more space. Okay, so this is what it would look like. So off that point already, we're looking east. Oh no, yeah, we're looking east. And 60 degrees south. This was about 43 degrees. We're not gonna follow that. So 60 degrees south would be around here. And I know it's gonna be kind of hard to look at because it's kind of intersecting with the other lines of the other displacement, but that's why I put it in a different color. It's gonna look something like this. We can label this as, I'll label it up here. Displacement 3, 30 meters, and we know it's east 60 degrees of south. It's going down there, so let's just label our axes again. And also we're gonna have to break this up into x and y components later. So this is the hypotenuse. The angle here is 60, which means this is the adjacent, which will be our x. This is the opposite, which will be our y. Okay, now our fourth displacement. And notice how I'm doing it in different colors, so it's easier to tell apart from all the lines that are intersecting. So displacement 4 is 30 meters east, and this is going to be a pretty simple one because there's no angle, so you don't have to break it up into x and y components. So off of this line, off of this vector's tip, we make another tail for the other vector. 30 meters east. East is just a straight line to the right. So we can say that is about 30 meters to the east. And this one will be pretty easy to label. You can just label it as D4 30 meters. And then finally our fifth displacement is 44 meters north 75 east. So north 75 degrees east. We're looking north. And we tilt 75 degrees east. And that would be about looking like this. Looking north. 10 degrees, 20, 30, 40, 50, and that is about 75. It's not going to be exact, but this is just like a rough sketch. So 75 degrees angle is inside. label our axes. Now we can label this as D5, 44 meters. This is the hypotenuse. This has an angle, so we're going to have to break it up into x and y components. The adjacent, and it's going up, so our adjacent is going to be our y in this case. And you're going to see why I'm assigning x and y's to the adjacents and opposites after this step. This is the opposite, which will be associated with our x. Now, another crucial step that you need to do is basically you're going to want to make a so I've cleared up some more space. Now what you're going to want to do is create a table with all the displacements, and this is how you're going to add them up all together. So this is what your table is going to kind of look like. Um, obviously it's going to be much longer because we got 5 displacements. And now what we have to do, and in my opinion, this is the most time-consuming part. You have to write all these displacements down and solve for the x and y based on what information is given about the displacement. Or no, not solve for x and y, but break it up into x and y components. So it looks like I'm going to have to make my line longer. And at the bottom we can put what is called the resultant, which is basically the total displacement of all these displacements added up. So starting with displacement 1, if we want to find how much it moved up across the y-axis, we're going to have to find the adjacent of this right angle triangle. And our angle here is 47 degrees. Our hypotenuse is 50. So for this we can use SOHCAHTOA. And to solve for the adjacent, we're going to use CA or cosine. What we're going to do is, so this is what the equation will look like. Cos 47 is equal to adjacent over 50. Rearrange to find adjacent, you get 50 cos 47. So let's just put 50 cos 47. This is for our y. So 50 cos 47, and it's going to be plus whatever the value we get is because it's moving north. So 50 cos 47 gives me about 34 plus 34.09. Now to solve for the x, we do the same thing. Instead we use sine. So you can do 50 sine 47. And this one will be negative because you can see in the x, in the horizontal component, it's moving west, and in west we labeled as negative, so this has to be negative. So I got minus 30, I got 36.56, but we're gonna label it as minus because it's moving west. Okay, that's one complete. Now second displacement, 22 meters west, 43 degrees north. So it's kind of hard to see with the third displacement intersecting with the second displacement lines, but that's why I put it in different colors. So our angle here is 43, and our opposite is our y, and our adjacent is x. If we want to solve for adjacent first, we're going to have to use cosine. So what we're going to do is 22 cos 43. And it's going to be negative because this is moving west again. So 22 cos 43. I got 16.08, so put negative 16.08. For the y, we do the same thing, but instead we use sine. So 22 sine 43. And it's going to be plus because this is still moving north. So 22 sine 43. And I got 15.000396, but I'm just going to put plus 15.00. Now third displacement, 30 meters east, 60 degrees south. This one is kind of a tricky one to look at, but we know our angle is 60. Our adjacent is our x and our opposite is our y. To solve for our adjacent, or otherwise how much it moved horizontally, we're going to have to use cosine. So we follow the same format. Cos 60 is equal to adjacent over hypotenuse, and our hypotenuse in this case is 30. Rearrange for adjacent, we will have to put in 30 cos 60. And it's gonna be positive because this is moving east. So 30 cos 60. I got 15 on the dot, so I'll just put plus 15. And then for y, we just do the same thing but with sine, so 30 sine 60. It's gonna be negative because this is moving south now. And south is negative. So 30 sine 60. I got 25.98, so I would put negative 25.98. This is an easy one. The fourth displacement, 30 meters east. So that is just going to be a straight line like we see here to the right. And east is positive, so we can just say this is plus 30. And there's no change in the y-axis. Final displacement, displacement 5, 44 meters north, 75 degrees east. So our hypotenuse is 44 and our angle is 75. Our adjacent is how much we moved in the y, and our opposite is how much we moved in the x. So if we're going to solve for adjacent, we're going to have to use cosine again. So we would do 44 cosine 75 for our adjacent. So this would be positive because it's moving north. So 44 cos 75. And I got 11.38, so I'm going to put plus 11.38. Then we do the same thing here, 44 sine 75. It's going to be positive again because this is moving east. And I got 42.50. So I'm just going to put plus 42.5. Now, one of the final steps is you're going to add all of these values together to get the final magnitude. No, not the final magnitude, the final x and y components of the resultant or the total displacement, and then you're going to use Pythagoras to find the magnitude of that line. So for our x, we have negative 36.56 plus negative 16.08 plus 15 plus 30 plus 42.5. And I get positive 34.86. Now for our y, we have positive 34.09 plus 15 minus 25.98 plus 11.38. And I get 34.49. So they're about almost the same, but a slight difference. Now, what you want to do with these x and y values for the resultant is you're going to make your own accurate triangle now. So for our x, we know these are both positive, so it's going to be, this one is going to be going east and this one is going to be going north. And usually I would start with the value that has the bigger value, so I'm going to start with the x this time. And so all you're going to do is make your own triangle. So you go 34.86 east, and then up 34.49. And now this is a right angle triangle. So now all we're trying to solve for is this line right here, which is the magnitude of the resultant. So let's label, we know this is 34.86. This is 34.49. Use Pythagoras. A squared plus b squared equals c squared. So in this case we can do 34.86 squared plus 34.49 squared and root whatever answer we get from that. And if we put this in our calculator, so 34.86 squared plus 34.49 squared, screw that answer, we get 49.08 of 49.03. And we're not going to round yet until the final answer, so we can follow significant digits. So this is the magnitude. To find the total displacement, displacement is a vector, so you'll have to have direction with it. So we're going to actually find what this angle is. And basically what I like to imagine this triangle to be is if you look at from the starting point, which is here, and the ending point, which is here. This triangle here is kind of a more accurate representation of how much they really traveled. This red line is the line that is going from the start to the end, and these x and y are how much they moved in the x and y. So you can kind of imagine it like that. Anyway, so that will tell you about the direction when we find this angle. So we'll just call it theta, and because the angle is touching this line, this would be the adjacent. This would be the opposite. Now that we have those, to find the angle, we can use TOA, which is actually inverse of tan divided opposite over adjacent. So if we put this in our calculator, we get roughly 44.6 degrees, and we're going to round at the end. But now we know our total displacement, so we can confidently put our final answer for the total displacement down here. And what I would like to do is do therefore the total displacement is, and let's round to two significant digits. So 49.03, that rounds to 49. So we can say the total displacement is 49 meters, square bracket, round to two significant digits for the angle. But also, what direction is this looking at? We're looking at east, and we're going up, but we're straying towards some angle north, because this is north, this is east, and our angle is 45. So we can say we're looking east, right? And then we go up 45 north. So our final answer would be the total displacement is 49 meters east 45 degrees of north. East 45 degrees north. I'm not gonna do this question because kind of running out of time, but the total distance traveled, this is the easiest question. You just, to distance has no direction, so you can automatically disregard all of these directions, and if there's no direction, then you just add all of these up together. This is actually answer B, and answer A would be all of these added together. So put it in your calculator, 22 plus 30 plus 30 plus 44. Oh no, I forgot the 50. 50 plus 22 plus 30 plus 30 plus 44 gives you 176 meters. And that's how you find the total displacement for a very complex 2D vectors problem with 5 displacements given with different directions. And our final answer was the total displacement is 49 meters east, 45 north. So thank you for watching, and I will make more videos on stuff like this. And please comment if you want more videos like this.